Thank you very much. Good afternoon, everyone. My name is Dániel Antók, and I work at the Center for Energy Research, which is part of the Hungarian Research Network. And in my presentation, I will shortly introduce the topic. Then I will move to tensile test experiments. Then I will speak about the simulation of these experiments. And finally, I will summarize the results. So our institute is involved with the lifetime extension of the Hungarian MPP called PAKS. And our research group performs structural integrity calculations. This new SIC methodology is based on nonlinear field theory of fracture mechanics. And we want to design such experiments that provide applicable data to support this new methodology. So in our calculations, we are using flow curves. So I will introduce you tensile tests in the next slides. These tensile tests have the nominal sizes at the gauge section of 8 millimeter width, 2 millimeter thickness, and 30 millimeter length. And the material is S460. This is a high strength structural material. We also printed a grid on the sides of the specimens to be able to follow the evolution of the deformation during the tests. And we also had a suspicion that the geometric imperfections, which are unintended, so these geometric imperfections have a role, plays a role on the formation of the necking during the tests. So we use the coordinate measuring system to measure all the surfaces of the gauging length and got a detailed coordinate map. Here on the right bottom picture, you can see as an illustration the thickness profile of a tensile test specimen. And as you can see, the nominal thickness should be 2 millimeters, but the average is 1.97. So it's a little smaller than it should be, but you can say it's not a big difference, but we will see it is. So the tests were carried out at the University of Dunaújváros on a Global universal testing machine, and we took 50 pictures every second, and we also measured the strain, the force, and the displacement. After the experiments were carried out, we had to further process the data, the strain, the force, the displacement, and also the photos. And after these processes, we were able to construct the flow curve of the material. We also used the Chungcho correction method to get more reliable values at high strains. So now we have the detailed geometry map of the specimen. We have good and reliable material properties, so we can build finite element models. In this presentation, I will show you 3 different models, and the only difference between these models is the geometry. The first model uses the nominal size, which is 8 millimeter width and 2 millimeter thickness at the cross section. The second model is also very similar because it's just uses the average size that was measured. It's a little smaller. And the third one is an advanced geometry because it uses the detailed coordinate map, which was previously measured. And these 3 models, I will show you in the next slides. At the left side, you can see the perfect geometry. This is symmetric and and the nominal size. And on the right-hand side, with the burgundy color surface, you can see that that surface was constructed using the measured coordinate map. It is those differences in the unevenness on the surface is very small, but it's there. And all the nodes of these elements were adjusted to that surface. So the third model contains all the measured unevenness on the surface. So let's see what are the results. The results for this is the equivalent plastic strain, the evolution of the plastic strain. And this is the first model, which is the nominal size. Everything is symmetrical, everything is perfect geometrically, and you can see that the results are also perfect. At the beginning, the strain is uniform, and it keeps symmetrical. The necking occurs at the middle of the gauging section. The second model is almost the same, because the only difference is it is a bit smaller. But the third model, which contains the very slight differences on the surface, is showing some difference. You can see that the strain field is non-uniform. The necking occurs earlier, and the necking is asymmetrical. It occurs close to one of the heads. So there is a difference. If you look at the force displacement diagrams, you can see here the nominal size. So this is the base. Let's compare the others to this one. This is using the measured average size. The shape is very similar, but there is a significant, the values are significantly lower. The third one follows the second curve, but the necking occurs earlier, so the failure will occur earlier. And here we are only comparing 3 models, but let's see where is the measured data. And you can see that it follows the third curve. The agreement is pretty good, and you can see that the noise of the measurement is smaller than the difference between the first and second one. So if you are using, if you want to simulate a test, you probably shouldn't use the nominal sizes. You should check every specimen should be checked before you break them, and use those data, the measured data, in your simulations. And if you have a detailed and advanced geometric model, it will lead to better results. Here you can see the digital twins, so you can see side by side the experimental and the simulation pictures. You can see that the evolution of the deformation is very similar, and that the necking occurs both in the simulation and both in the experiment near to one of the heads. So what did we learn? What is the moral of the story? Small specimens that suffer large and nonlinear deformation during tests are sensitive to geometric imperfections. These geometric imperfections are unintended, so maybe it appears when you manufacture the specimens. And such tests should be designed and carried out with great awareness, and not just tensile tests, but any test that uses small specimens and suffer large deformations. And I hope that I was able to show you this digital twin-based analysis, and we were able to better understand the nonlinear deformation phenomena in our tensile tests. So thank you for your attention, and I'm waiting for your questions.